this is about how to think about average Hamiltonian theory. I want to give you a background. And the goal of giving you, or the reason for describing all the details of the average Hamiltonian theory is so we can have an understanding of how cross-polarization works, how spin lock works, to be able to derive some of these commonly used as NMR pulse sequence elements, right? And then also to get to ReDOR, which is, for me, I think the simplest and most robust dipolar recoupling sequence. So the notes I have here are taken from a graduate level MIT course that I gave 5 years ago. And, you know, I took about maybe 20 lectures to talk about the quantum mechanics of NMR. And there's no way that I can go through all of that here in just 2 hours or so. In the first about 10 pages of this set of notes, this is about 33 pages, it's the NMR Hamiltonians and density operators. If the PowerPoint slides that I had yesterday seemed a little jumpy, some of the proofs are not given, then they're given here. All right, so if you, for example, want to work out where the equilibrium density operator, the expression comes from, you know, the proof, some of the mathematics, they're here. All right, so I think this set of notes really try to go through all the proofs. Yeah, so, all right, so I go to about page 10. Skip this. And here are some matrix algebra background. We want to have expressions of two spin product operators expressed in, you know, in terms of 4x4 matrices. I have that spelled out. Okay, so this is where I would like to start. Average Hamiltonian theory. This AHT theory was developed by John Wall and Ulrich Heberlein in the 1960s. It is a mathematical formalism to analyze multiple pulse NMR sequences. Basically, when you put out a train of RF pulses with certain phases and with delays in between, how do you think about the cumulative impact of these pulses on your spin states, on your density operators? The idea is to try to calculate the average Hamiltonian due to the combined effect of RF pulses as well as local fields meaning dipolar couplings, chemical shift, all of these spin interactions. And once you have that average Hamiltonian, then you can say, okay, now I can apply the von Neumann equation and see how my rho, the density operator, would evolve in time under that average Hamiltonian. So that's the goal, all right? And so you want to think about your total Hamiltonian of the spin system in three categories. One is the big Zeeman interaction that you can say I transform that away by going into the rotating frame. And then you have the RF pulses, all right, all your train of pulses complicated. And then you have the local fields. And usually you care about the dipolar couplings, the chemical shift, the quadruple couplings. But if you have a bunch of these RF pulses with certain phases, how do you deal with that? These RF pulses can often be stronger than your local field. The omega-1, the B1 field strength is in the tens of kilohertz, 100 kilohertz, they dominate the local fields, right? So the idea of the average Hamiltonian is to allow us to change or move into a frame that's dictated by the RF pulses. And this is the interaction frame or interaction representation of RF pulses. And then in that interaction frame of the RF pulses, the effect of the RF pulses is gone, and you transformed your local fields of interest in that interaction frame. It's an interaction frame representation of these local fields. And then you average all of these local fields. That's what you want. This is the first order average. In principle, you have higher order terms, but usually under some conditions, you might not worry about it. So this idea of transforming away the impact of the RF pulses should sound somewhat familiar to you. It is almost like what we do going into rotating frame, because you say, well, I don't want to think about the B0. I want to go into the frame dictated by the B0. So the rotating frame is the interaction frame of the Zeeman, the B0 interaction. I want to do something analogous. Now I want to go into the interaction frame due to the RF pulses. So that's what this section is trying to say, that we want to go into a new frame of reference where the RF pulses no longer appear directly. For most of these applications of average Hamiltonian theory to specific pulse sequences, you want to engineer your pulses. You know, you have a train of pulses. You usually build them so that a cycle of these pulses come out average to be cyclic or zero. So you don't have the net effect of the RF pulse on the spins. You don't have to worry because of the cyclic nature of these RF fields. All right, so we're going to have to first deal with mathematically how to work out the interaction frame transformation. And I want to start by doing the familiar example interaction frame of the Zeeman interaction, which is the rotating frame. Okay, so here in Lamo precession is something we talked about geometrically, thinking about gyroscopic motion. If I want to write that down mathematically, that is basically saying, okay, I take my initial magnetization, initial density operator, rho at time zero, and due to the B0 field, if you recall the von Neumann equation with this d rho dt equals minus I commutator of h rho, the formal solution of that von Neumann equation is something like this. We have rho of t at time t is the rho zero being sandwiched by the propagator e exponential operator e to the minus plus h0t, h0 being the Zeeman interaction. So that's the formal solution to the von Neumann equation. And then you can spell out what h0 means. It is the gamma b0, and then they have a spin operator iz. So that's all fine. So that expression of rho t in this format corresponds to transformation into the rotating frame. So now in that frame, the magnetization would appear static because the frame is rotating. This is the rho of t, its time evolution. And the transformation to the rotating frame is written down separately. It's a little bit different from what you see in the equation 1. So the mathematical procedure for transformation into an interaction frame involves taking the rho of t, which is in equation 1, is in the laboratory frame, and then you have to dress it before and after with e to the, again, exponential operators, e to the I omega r, IZT in the front, and then the opposite signed term in the back. This omega r, the big R subscript, is the frequency of the rotating frame. So this is the procedure or the definition for how you would create a rotating frame or interaction frame expression of the density operator. Okay, so the rho of t in the center here without a subscript is the laboratory frame version. That is my normal time evolution. And rho of r is the interaction frame, rotating frame representation of density operator. Equation 2 is the density operator in the interaction frame of the Zeeman interaction. Okay, then you can combine these two equations because you say, okay, I know rho of t is equal to this, and I have now a transformation equation. Then I can combine the two and say, okay, then rho of r, interaction frame at time t, is equal to rho of 0 sandwiched by these two exponential operators, where exponent has a combination of omega r minus omega 0. That's their frequency. So why do I leave rho of 0 in the middle as if this is a laboratory frame term, right? I don't have a subscript r for it. Well, at time 0, rho of 0, whether it's lab frame or interaction frame, it's the same. So I can leave it alone like this. Having this expression is useful to get a little bit of insight because you can say, well, I can choose my rotating frame frequency, omega r, to be a little different from omega 0. And if it's a little different, that's the net, that's the little offset, right, that I showed you in picture in the first lecture. This rotating frame that we're all quite familiar with gives you an idea how you would mathematically handle the transformation into the interaction frame, interaction representation. All right, so now let's make it general and say I want to do interaction frame transformation for any Hamiltonian, and the Hamiltonian that I really care is RF Hamiltonian. What happens when I have so many pulses? So in general, for a Hamiltonian consisting of a large H0 and a small H1, let's say this way, H1, the little one, can be transformed into the interaction frame of H0 by this equation. So I care to take my small interaction local field and take that into the interaction frame defined by the bigger one, H0. So that then the definition is take the H1 and sandwich it by this propagator or exponential operator before and after, and pay attention to the sign of the exponent. It's positive sign in the front, a negative sign in the back. Okay, so e to the I H0t, e to the minus I H0t. Now that gives me a new H1 in the interaction frame, and I will represent the interaction frame quantities with a tilde at the top. So that's my notation. And I'm going to do the same thing, this transformation for the spin state, the density operator. I have a row of T in the laboratory frame, and I'm going to dress it by these exponential operators with these signs, e to the IH0t, e to the minus IH0t. That creates the density operator in the interaction frame, rho tilde. And in that interaction frame, the density operator will evolve in time following the same von Neumann equation. So you're going to see the same kind of expression, d rho tilde dt, and it's going to be equal to minus I and commutator of the H1, the new interaction frame, small interaction, H1 tilde, commutator with rho tilde. When you do this, well, not the time evolution equation, but this interaction frame transformation of H1, you see you're going to now create time dependence to H1. Now, if you recall, when we solved the von Neumann equation, we said in the lab frame, okay, von Neumann equation, we say you have these rho zero with an exponential operator before and after. And then I said dot, 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 skip some of these algebra. The result is that my row of T will acquire time dependence, cosine sine. You have one term, Ix, and then there's another term, commutator, there's a sine omega T. It's always going to be this kind of sinusoidal oscillation, right? That's mathematically how it generally works out. So you can see when you do this interaction frame transformation for H1, the H1 is going to develop these oscillations as well. It's going to pick up cosine sine, right? So it's the same math. Then that leads me to make the following statement. When you have now oscillations of H1, then the components of H1 that don't commute with the big interaction H0, those are the ones that will have this time dependence. And so if H0 is much greater than H1, which is our starting point, you know, H1 is basically a perturbation to the large interaction, then that time oscillation will be really fast because H0 is a very strong interaction. The corresponding frequency is going to be hundreds of megahertz, and that time oscillation due to H0 will be much faster than any time dependence of H1 itself. Even if your H1 is time dependent, let's say my RF pulses are, you know, time dependent, but it is generally slower in time dependence compared to the H0 time dependence. So the effect of these non-commuting terms of H1, those terms that don't commute with H0, will be averaged to zero, just because that cosine sine, that oscillation is fast. So the time averaged H1, now in the interaction frame still, is then equal, in this equation, equation 7, you can write this as H1 average, and there's still the tilde because I'm in the interaction frame. And I'm going to put a superscript 0 here to indicate that it's a simple average. I'm not worrying about any higher order terms that may happen. I'm just going to worry about the average, the simple average, okay? So this is the first order. And this, well, if I take equation 4, mathematically, you just say, I put a bar there. That's my time average, okay? So this is what you're supposed to calculate. But the point is now the average Hamiltonian should be time independent. So the non-commuting terms will be gone. Only the commuting terms will stay. Remember, this is the picture I had in the first lecture where you say I have a big B0 field pointing this way, and then I have sort of small interactions, this and that. And I said, truncate the terms of the local field that don't commute with B0, and only the components that are parallel to B0 will stay. And this is basically that idea, but more mathematically spelled out. Okay, so you see this is equation 7. It is the definition of truncation of H1 by H0, and the time averaging retains only parts of H1 that commute with H0. Okay. So, well, now I'm happy with a simple average Hamiltonian of H1 in the interaction frame of H0. And then I say, well, my density operator in the interaction frame, rho tilde, should evolve in time as dictated by that average Hamiltonian, right? So it's again this kind of expression, this rho tilde 0, which is, by the way, the same as rho 0, being propagated by the average Hamiltonian. And it's going to follow this kind of expression, again, propagated before and after, and it's exponential operators with now the average Hamiltonian being in exponent. So this is the step that has changed. I'm replacing the general H0 by a time average Hamiltonian. But in doing the normal time evolution, which is following the von Neumann equation, just again pay attention to the sign of the exponent. The propagator before the rho 0 has this negative sign. So there is a sign difference. All right. When you're done with the rho of t in the interaction frame calculation, we say, well, in the end, we would like to know the density operator in the laboratory frame. I need to step out of the interaction frame. And the way you do that is you flip the equation that lead from rho of t to rho of tilde t and just multiply both sides of the equation with the opposite signed exponential operator. If I multiply both sides of the equation with e to the minus IH0t in front of the term, and then after the term with e to the plus IH0t, then you see what happens on the right-hand side. You'll be left with rho of t, which is this, and then on the original left-hand side, rho tilde t acquire these terms. Okay, do you see that? All right, so that's what I'm doing. I'm shifting the way I think about or write the density operator. So now density operator in the laboratory frame is equal to these three terms multiplied. And then I can go a little further. I can substitute the expression 8 into expression 9, and I expand the middle. Then you can see what that does is for me to combine these two exponents. In front of rho 0, I would have e to the minus I, the H0, the large Zeeman field, and then plus H1 tilde average. All right, and then the propagator after rho 0 is just the opposite sign version. So by stepping into the interaction frame of the large interaction, H0, I can calculate the average Hamiltonian of the small interaction H1. And once I've done that, I can then come back out of the interaction frame, going back into the laboratory frame, and consider rho of t, how it evolves from the rho of 0, the density operator at the initial time. And you see that what happens is basically it's evolution under the combined effect of H0 and then that average Hamiltonian. That average Hamiltonian is what you're really interested in. So this equation for rho of t differs from the normal expression of rho of t. If you never worried about interaction frame, you would just say, well, I have a rho of t evolving under the total Hamiltonian H0 plus H1, and that's what you have in equation 11. And the only difference between equation 10 and 11 is that this H1 has been replaced by the average Hamiltonian. So basically, transformation to the interaction frame amounts to replacing the H1 by its first order time average. I will pause here and say that when I show you later how to think about spin lock, heteronuclear decoupling, cross-polarization, all of these things, often it's good enough to not worry about the calculation of the density operator rho of t. It's more important just to know what is the average Hamiltonian H1 tilde average. If you know that, it already gives you most of the insight you need, because how magnetization or spin state evolves under Hamiltonian, we kind of have an intuition. This is von Neumann equation solution to the von Neumann equation. You know that. What is harder to get is what exactly is the average Hamiltonian. So for example, if I say under spin lock, let's say you're spin locking on a proton and you have all sorts of proton-proton dipolar coupling, and you're applying a strong spin lock. Is the proton-proton dipolar coupling still there, or is it gone? And for that matter, you can also ask, under spin lock, is the chemical shift interaction still active, or is it gone? Average chemical shift, is that 0 or is that finite? That's the kind of question you want to know. So once you know that, I often don't need to step to the next complicated rho time evolution calculation, okay? But mathematically, you see how one is supposed to do the calculation. So that was the general presentation of how to define and transform into this interaction frame of a certain Hamiltonian. So now I want to be specific and talk about how to transform into the interaction frame of the RF pulse. The interaction frame is very useful for calculating the effective local fields, effective chemical shift, dipolar coupling, J coupling, or quadrupole interaction under the RF pulse. Okay, so now these RF pulses are generally stronger than the local Hamiltonians. So now I'm going to write omega 1, which I usually use to denote RF field strength, much greater than omega, let's say I or IS or whatever interaction you have. So then now let's transform the local fields, nuclear spin interaction Hamiltonians into the interaction frame of the applied RF pulses. So, all right, so for a Hamiltonian consisting of HRF equals, let's first write down what is the RF pulse Hamiltonian at all. I would write it as omega 1 times I alpha. Omega 1 denotes gamma B1. That's the magnitude of your RF pulses. It is not the frequency of your RF pulse. Okay, it's the strength, it's the magnitude. I alpha, this alpha can be X, Y, Z, depending on which direction you want to apply your pulse. And this is usually, okay, my notations, my subscripts are not particularly great. Let me just say this HRF is larger than H chemical shift, H dipolar coupling, and so on and so forth. All right, this one is a little bit confusing. So now let's transform the local spin interactions into the interaction frame of the RF Hamiltonian. And so you do the same, apply the same definition of that transformation. H1, the local field, is going to be sandwiched by these propagators of the RF interaction, RF pulse, e to the I H RFT before, and then e to the minus I H RFT after. So that gives me the H1 tilde. Okay. Okay, so this is, you know this, the effect of the pulse is to rotate the nuclear spin interaction. So this equation, it looks mathematically now familiar and trivial, but physically it's interesting because it says, instead of thinking about your RF pulse, rotating your spins, your magnetization, think of your RF pulse as rotating your interactions, your chemical shift, your dipolar couplings. I'm no longer rotating magnetization, the spin state, I'm rotating interaction. So that's the first time I think you, in my lectures, you see this. All right, so the effect of these RF pulses is to rotate nuclear spin interactions in a way which is kind of analogous to the von Neumann equation. It's Hamiltonian's rotating magnetization density operators. But the sense of rotation is opposite. There's a sign change, right? So if I tell you before everything's left hand, for this you kind of have to do right hand. All right, so we can designate the propagator of the RF pulse. Okay, this is just notation. In some textbooks, you see that RF pulse is written as P, defined as e to the minus IH RFT. And more common notation is to write propagator U, subscript RF. Whichever way you want to use this notation, it recasts equation 13 as H1 tilde T equals P. If you use P, then it's P to the minus 1 H1P. All right. Don't worry about the notations too much. Just keep track of the concept. But the point that we really want to get to is that we want to figure out the average H1 in this interaction frame where the effect of the RF pulses have been transformed away. So I really just need to think about what's the average local field. And so the average notation-wise is H tilde. I put an average bar at the top. And mathematically, what you do is to take equation 13, e to the I H RFT times H1 times e to the minus I H RFT. And I have to average that over time during which your pulses are active, dt, and then you integrate. And this is exactly what I'm going to do to understand spin lock, understand decoupling, understand cross-polarization, because you basically have a continuous irradiation on one or two channels, right? So I'm going to have to work out integration from time 0 to TC, the cycle time. Okay, this averaging requires that the RF pulse sequence is periodic over a cycle time, TC. So when it's continuous irradiation, which is what I want to focus on, it's easier. So that's what I'm going to treat. All right. If it's discrete pulses, sandwiched by free evolution times, it's a lot of work. I've talked about that. That's like a classical Wakuha homonuclear decoupling sequence. And it's also interesting to go through. And if you're interested, I recommend you to look at chapter 3 of the Schmidt-Rohr and Spies book, where it's laid out exactly how you would prove. You have a pulse propagator P going different directions because of the pulses X, Y, Y, X, and so on and so forth, right? So due to the impact of these pulses, the free evolution in the windows, right, change direction. Instead of evolving under the Zeeman always Z, these pulses are switching the direction of the evolution, the guiding field. So that's where this notation P and so on gets applied quite a lot. But if it's continuous irradiation, things are simpler, and I will present that to give you some insight. So for multiple pulse sequences, we can determine the interaction frame spin Hamiltonian visually. That gives you a sense of how to treat multiple pulse decoupling sequence or composite pulse sequences. You determine the interaction frame spin Hamiltonians visually by toggling the frame of the internal Hamiltonian. And how does this toggling work? You would flip the interaction frame with the RF pulses in a rotating frame around the axis of the pulse, and then the axis of the interaction representation coordinate system that is parallel to the z-axis of the rotating frame is the direction of the H1 tilde, and then you add up all the H1 tilde's directions for all periods, all the discrete periods, to obtain the average Hamiltonian. So if you imagine 4 or 8 pulses, imagine these pulses are infinitely narrow, infinitely short delta pulses, then it's only the windows between pulses that you have to add up all the interactions, and that's what you do. This is kind of a recipe. There's a second part to this transformation into the interaction frame defined by the RF pulse, and that is, again, you have to deal with the density operator describing the magnetization, and it's the same idea. You say rho tilde now is equal to rho in the rotating frame, sandwiched by e to the I HRFT before and e to the minus I HRFT after. And then the equation of motion is again the von Neumann equation, but everything done in a tilde or interaction frame. And then you can go on and calculate. What you would get in this procedure is similar to what I showed in equation 11 and so on. All right, so this is a bit of a repeat. All right, let's get to the bottom line. The bottom line, skip some of that details. Rho of t in equation 18, A or B, in the end gets to this point. It says rho of t is evolved from rho of 0 at time 0 by 2 sets of propagators. There's the RF propagator, URF, which corresponds to e to the minus I HRFT. And then there's the U1 tilde. The U1 tilde is what you really care. That's the local spin, nuclear spin interactions expressed in your interaction frame, and you take the average Hamiltonian to evolve your rho of 0. Okay, so skipping here to equation 20, work out the average Hamiltonian, and then you see rho of t should be evolved from rho of 0 by these terms. And so now what happened compared to equation 18 is basically I'm going to just take the average Hamiltonian instead of the full complicated form of U1. But when you look at these expressions, your rho of 0 is dressed by 2 types of propagators. There's always the RF propagator along the way. And so this is where we need to invoke cyclic sequences. Cyclic sequences, what is cyclic? URF is a bunch of these e to the minus IH RFT. This T is a notation, the timing Dyson operator, to say that, okay, if you have multiple pulses, you've got to keep doing this to represent all the pulses. But the point for cyclic sequences is that in the end, the whole thing over the cycle time of TC, this U is 1. So in a simplest kind of 4-pulse Wakuha pulse sequence, you have 90-degree pulses, 4 of these, and the phases are such that they cancel. So XY minus X minus Y. So in that sense, this is a cycle, right? So the impact of all the pulses together is gone. And for doing continuous irradiation, such as spin lock, you put your pulses out for hundreds of microseconds or milliseconds. And so over the kind of long duration, and your strength of the pulse is usually, tens of kilohertz. So you have gone through integer multiples of your basic cycle time. All right, so the cyclic sequence condition is usually satisfied. Okay, given that URF for cyclic sequences is equal to 1, then of course, rho of t gets very simple. It's basically equal to, you can drop the URF part, and then you can just have the e to the minus IH1 average Hamiltonian times TC. There's a little bit more detail. I skipped over some detail about how the average Hamiltonian, the H1 tilde average is equal to an infinite series, and this is Magnus expansion, and then there's the zeroth order, first order, second order, so on and so forth. You get a sense what these higher order terms look like. They usually involve commutation of the local fields at different times, T1, T2, and there's higher order commutators and so on. But we generally just worry about the lowest order average Hamiltonian. That's just a simple thing. I'm going to add up the H1 tilde over the cycle time with 0 to Tc. I think I can skip this. I already told you that the sign of rotation to transform into the interaction frame is the opposite sign from the way you would work out the solution to the von Neumann equation. The solution to the von Neumann equation involves the exponential operator in the front is e to the minus I something, and the transformation into the interaction frame uses opposite sign, and it's the term in the front is e to the plus I HT. Just to give a summary of this average Hamiltonian theory without the mathematics, basically when you have RF pulse sequences and internal spin interactions that are periodic over a cycle time, your RF pulse sequences have to be cyclic, and the net rotation produced by the RF block is 0, then applying the average Hamiltonian theory is really convenient. It converts the problem of finding the propagator U for the whole thing. The whole thing is very complex. You have to think about RF pulses, you have to think about local fields. Then this problem simplifies to finding just the local fields average term in the interaction frame of the RF pulses. So the effect of the RF pulses is transformed away. So let's apply this mathematical formalism to understand some simple and very common NMR pulse sequence elements. The first application I want to talk about is chemical shift interaction, how it behaves under a spin lock. The examples that I want to show look kind of similar. You say, all right, I'm going to apply a 90-degree pulse. Maybe I want to do this along minus y direction, and it doesn't matter which channel, just one channel. And I'm going to now do spin lock, and I'm going to choose the continuous irradiation that comes out in a certain direction. And that direction better be perpendicular to the initial 90-degree pulse. And it doesn't matter plus x, minus x, that doesn't matter. Okay, so I want to know what happens due to this spin lock term. And you can ask, what is the effect of the spin lock on the chemical shift interaction? If there's no spin lock and you just detect right after that 90-degree pulse, you know you're going to detect the chemical shielding interaction. And that has to do with the fact that in the rotating frame, when the B0 field is transformed away, there is still chemical shift evolution. The chemical shift interaction is omega CS, chemical shift frequency, times IZ. And so your X or Y magnetization will evolve or precess around that interaction in the rotating frame. So chemical shift would be measured as your time signal. But if you have a spin lock, then let's think about the Hamiltonians. The chemical shift interaction, HCS is omega CS times IZ. This is so true. And I have an RF Hamiltonian. And as I sketched out, I want to think about an X spin lock along the X direction with a field strength of omega 1. This is how strong it is. So equals gamma B1. And I'm going to now take the average Hamiltonian theory, transform the chemical shift interaction into the interaction frame of the RF pulse, the X pulse. And what that means is I take the omega CS IZ in the middle, and I have to apply the RF propagators. So e to the I omega 1 IXT in the front, and then minus sign in the back. Okay, that's because the RF Hamiltonian is omega 1 IX. So, all right, so what's the outcome of that calculation? This is where you have to keep remembering how to solve this kind of exponential operators multiplied onto a spin operator. This is the same way you solve the von Neumann equation. There's going to be cosine sine sinusoidal oscillations. So it always comes out this way. So the spin operator in the middle here is IZ, and it is affected by IX before and after. The way you think about it is, okay, IZ is my initial term. That's the term, spin operator, that's going to pick up a cosine modulation. And then the commutator IZIX is going to give me IY. You have to be careful to get the sign correct. But otherwise, the fact that it's IY is unambiguous, and there's no imaginary anything. And that term is going to pick up the sine oscillation, sine series. And the frequency of these oscillations, as you could imagine, is going to be the omega 1. It's how strong your spin lock field is. So this is like the way you would apply the product operator formalism to work out the time evolution of the density operator. There's just a sign switch. Okay, so now that is my HCS tilde, and it still has the time dependence. What I really care to know is the average of that. So let's do the average. And what that means is I need to take this time dependent, this oscillation, and integrate over a certain time, how long your spin lock would be, 0 to TP. And then because I'm doing average, I also have to divide by time, 1 over TP. And the omega CS, that is a frequency term that can come out of this in front of the integral. It's a little bit of math to work through. And inside this, you have to deal with the integration of cosine sine, which just changes from cosine to sine, sine to cosine, which is all fine. And then you integrate 0 to TP. This is the place you have to think about it a little bit. If my spin lock time is exactly equal to integer multiples of the inverse of the RF field strength, then no problem. My cosine sine all average to 0, because these are cosine sine omega 1t. Okay? So then this is naturally 0. But if my TP goes out very long and I'm not exactly watching whether it is exactly integer multiples of the inverse omega 1, then it doesn't matter very much, because even if it sticks out a little bit, it's a very, very tiny portion compared to how long my TP is, because in the end, I have to divide by TP. That's what average means. So this still approaches 0. So the average chemical shift interaction during spin lock is 0. Okay. Think of omega 1 here. Let me just give an example. Suppose omega 1 over 2 pi is 50 kilohertz. The cycle time due to this is 20 microseconds. You normally would apply spin lock on the order of a few milliseconds, hundreds of microseconds. So you would have tens, if not hundreds, of these basic units. If your spin lock happen to be ending at exactly integer multiples, cosine sine average to 0. If you stick out a little bit, doesn't matter, because you're taking that little bit non-zero and divide by it. That's all. Okay. So spin lock averages the chemical shift interaction to 0. There's no chemical shift evolution during spin lock. That's what spin lock means. You're locking your magnetization, it's not running away. So without the spin lock, you would otherwise normally say after 90 degree pulse, putting the magnetization along a certain direction. If you want to do X, that's fine. This is my X, this is Y, this is Z. Then usually that's the free precession. The free means H0 is then again down, controlling you, and you have to run away. But by doing the spin lock along the X, this is my RF spin lock field, or omega 1, then this magnetization will no longer precess. It'll be locked. So the average Hamiltonian of the chemical shift interaction as calculated by transforming into the RF interaction frame comes out 0, and that explains why the spin is actually locked. All right, so now let's take this general approach, again, very simple, to explain something that we use all the time. And if you want to know why does it work, right, heteronuclear decoupling by continuous irradiation. The pulse sequence looks almost exactly the same, but usually what I have to do in solid state, say, okay, I get my magnetization somehow over to an X spin carbon, and I do CP, okay, and then I'm ready to detect the carbon, right? Or whatever channel you want to look at, whatever nuclear spin you want to look at. But your detection always has to be done under the protection of dipolar decoupling. Unless you're studying inorganic systems with no protons around. Otherwise, typical organic compounds, bioorganic, you have lots of protons. You have to get rid of the impact of the proton, right? To get narrow lines. All right, so this dipolar decoupling module is nothing but a continuous RF irradiation along a certain direction. And the most old-fashioned way is you don't even change the direction. In the modern way, you change direction. But let's just think about continuous irradiation along a certain direction. It doesn't even matter very much what you do. So why does this work? Why does this continuous irradiation on a background channel remove the dipolar coupling to the spin that I'm looking at? You can ask that question. And we can answer that by using this average Hamiltonian theory without too much trouble. Again, I'm not solving the role of T evolution. All I want to think about is average Hamiltonian. And I want to show that the average dipolar Hamiltonian is 0. And we can show that. So this is this part. So, okay, the heteronuclear dipolar coupling in laboratory frame, HIS, is proportional to IZ/SZ. This is a truncated form of the dipolar Hamiltonian. And all the spatial terms are encapsulated in this term, omega D in the front. That's the place where you have the gamma I, gamma S, 1 over R third. You have the orientation dependence and all of that. Okay, we don't worry about it. Let's consider the effect of a continuous RF pulse, HRF, equals omega 1 IX. Again, just point it along X. If you point along Y, it still works, doesn't matter which direction. And the strength of the RF pulse, again, is omega 1. And that's going to happen on the I channel. My I spin I is the proton, is the abundant spin. What I detect is S. The continuous I pulse affects only the I spin operator, right? So that's fine. So now let's think about, I'm going a little bit fast here, I skipped a step, but first we have to transform the dipolar Hamiltonian into the tilde frame, the interaction frame, and that transformation use basically the same kind of math as you saw here, right? You do the same kind of e to the I, HRFT in the front and the back, and you can see now the SZ is untouched by the pulse. Only the IZ will change, and it's again going to pick up these cosine sine terms. So it's going to be IZ cosine omega 1t, and then it's IY because you're applying X pulse, so the commutator is IY sine omega 1t, good. And then this whole thing is going to multiply SZ because you're dealing with the IZ/SZ Hamiltonian. All right, so this is the way that the tilted form looks like, and then I'm going to have to average that, integrate that over the duration of the decoupling, so 0 to TP, and I'm going to do the same math, and I still keep the SZ, and I have the IZ terms, and so on and so forth. And so for exactly the same reason that you saw, chemical shift has vanished under spin lock. Heteronuclear dipolar coupling, the IZ term is starting to basically oscillate, and it's going round and round and round, the IZ, Y, and just, right? If you're doing the pulse along the X, then the dipolar Hamiltonian is just going to toggle, keeps doing this, and you're averaging that over a certain time, it's going to average to 0. So IZ/SZ will also vanish, and that's what you want. The heteronuclear dipolar coupling will vanish to 0. All right, so the next thing I want to talk about is homonuclear dipolar coupling under spin lock. So again, I have the same spin lock sequence, but I want to put it on the abundant spin that has a lot of dipolar couplings, proton-proton. And where do you apply this? I'm building my case step by step to CP, cross-polarization. During CP, you're applying continuous irradiation on both proton, abundant spin, and a heteronuclear spin. So I want to consider the problem of, okay, what happened to my proton dipolar coupling? You have lots of protons around, and then you have a rare spin carbon occasionally, if it's natural abundance 1% of the time. Even if you uniformly label your protein or whatnot, it's still not as abundant as proton. So while you care about proton magnetization transferring to carbon, that's the purpose of CP, you can ask what happened to, all of these interactions. Are you removing them, or are they still alive? So that's an interesting question you should think about. And all right, so let's work out how this looks like. Homonuclear dipolar interaction under spin lock. This is a little bit more work, but it's still relatively intuitive. So first, let's write down homonuclear dipolar interaction, HII. Okay, my notation is not great. We might call it IJ. Let's just say IJ equals omega D. Now remember, the Hamiltonian for homonuclear interaction, the truncated form, is 3IZJZ minus I dot J. All right, so IJ to represent the same spin type but maybe different chemical shift. Anyways, so 3IZJZ minus I dot J. I would like to create a notation of HZZ for this laboratory frame, homonuclear dipolar coupling, and it's done for a purpose later. And the subscript of ZZ simply denotes the fact that the first term, the spin operator is IZ in the laboratory. Okay. All right, so then I need to transform my homonuclear dipolar coupling into the interaction frame of the spin lock. And in this case, I think the spin lock is again along X. And because I have two spins, I have IZ, I have JZ, they're the same type of spin, both protons, then each one will be impacted by this spin lock pulse. And if it's the spin lock is along X, my Hamiltonian is going to start from Z to Y to minus Z minus Y, just keeps going. So each of the IZ terms become IZ cosine omega 1t plus IY sine omega 1t. You do the same thing for the J, and that's good. But I thought J, that's a scalar product, that's not affected by any of your pulse directions, so nothing happens to that term. So then you multiply out these two sinusoidal series, you collect the terms, you find IZJZ cosine square, IY sine square, and then you have sort of the cross terms, IZIY, and so on and so forth. Okay, so now we have to simplify these things somewhat. Let's see, the simplification comes from taking the ZZ and YY terms, put them together. What I'm doing here is I'm taking the sine square term and write that as 1 minus cosine square, so that you can see what's happening here. I'm skipping some of the derivation details. All right, what happened to cosine sine here? Why do I not have the cross terms anymore? Here, the cosine sine product is sine of 2 times that angle. And when it's a simple sine of anything, and you do time averaging or integration, it vanishes. The only time that a geometric term doesn't vanish over integration is when you have squares. And I can explain this by, if you remember, half angle relationships, things like this. But if you don't remember, that's okay, because I can sketch how it looks. And the sketch is that a simple sinusoidal oscillation, well, whether it's a sine or cosine, this is cosine, and then you get sine. I'm gonna make mistakes about the periodicity, but anyways, something like this. When you average cosine sine, you know it's gonna get to 0 because it hovers, averages around 0. But when it's sine square or cosine square, you see this is my 0. If I take this sine function and square it, you know what's gonna happen is it's gonna do this. Everything is positive, as it should be, right? So this is a sine square function of whatever angle. Cosine this is, sorry, this is cosine square. Sine square will start here. So whenever you deal with sine square and cosine square in NMR, you know pretty quickly that the average or integral won't be zero. In fact, it's 1/2. Okay, so that's what I have here. So these cross terms, cosine, sine, and so on, they drop out, but the sine square, cosine square, they will remain. And so here, there's some algebra to work out details. But you basically get 3/2, and then IZJZ plus IYJY, and then you still have that minus I dot J. Now, I dot J, what is I dot J? It's a scalar product, and it is the sum of these three terms. So if you take that and re-express what happens here, you see that IZJZ plus IYJY is basically I dot J minus IXJX, right? And then I have IXJX coming out, and I group the terms and so on. I'll find this, all right? So you can, if you're curious, work out some of the algebraic details. But this basically looks almost like the laboratory frame homonuclear dipolar interaction, except that instead of ZZ, I've got XX. And then instead of just omega D in the front, I get a minus omega D times 1/2. And so basically the average homonuclear dipolar coupling under spin lock has half the strength of a laboratory frame dipolar coupling, and it points in a direction which is the spin lock direction, X direction, HXX. I can write it this way. So the average Hamiltonian has half the size of the lab frame one, and it's oppositing sign, and the direction of that interaction is along the spin lock. So the bottom line is homonuclear dipolar coupling is not average to zero. It doesn't vanish. It's still alive. It's just slower by a factor of 2, and it's oppositing sign. And the fact that it's opposite is actually quite nice, because you can then engineer pulse sequences where you say, I'm going to take 2 times the spin lock, and then I'm going to mix it with 1 time the free evolution, and they can start to cancel the homonuclear interaction in that way. And that's the idea that Alex Pines had many years ago. He calls it magic sandwich echo. He could generate an echo by combining spin lock with free evolution in a 2-to-1 fashion. The spin lock weakens the coupling by a factor 2. So he makes that up by having 2 times as long. And that negative sign is very useful, because if you don't have that negative sign, you cannot cancel. So he wants to get rid of homonuclear dipolar coupling by doing this magic sandwich echo. So homonuclear coupling is not averaged out to 0. And that's why in CP, unless you're spinning very, very fast and you start to really remove these things, but in most standard solid state NMR, you use the fact that the proton-protons are still coupling to each other in order to maximally transfer magnetization to the rare spin, because if you say I have my proton here directly bonded to a carbon and I transfer, well, then you cannot transfer all that much. At best, at equilibrium, you share half of the proton magnetization with that carbon. Well, that's not helping a whole lot. What you really want to do is to, as soon as this proton magnetization is depleted a little bit by this, the other protons can relay magnetization to this through that dipolar coupling, which still exists. And then you can fill in the reservoir here. And then this will then give magnetization to this. These other remote protons can, in principle, also do CP to this, but it'll be more work. And it's harder because the coupling will be just weak. Heteronuclear coupling is weaker, but the homonuclear coupling is pretty strong. And then this dense network of protons basically keep filling this one in order to pump the magnetization over to the rare spin. And so that's why in classical, let's say unlabeled carbon-13 natural abundance system where the carbon doesn't happen very often, then you have a huge excess of proton relative to the spin you want to polarize. Then that cumulative effect in the end basically says this one carbon can get almost as high of a magnetization as any one of these protons because you have a large excess. And so that's why CP cross-polarization enhances the sensitivity of the rare spin compared to doing the simple 90-degree excitation of this by the ratio of the gamma. The CP enhancement, this formula that you probably see, you say, oh, CP enhanced my sensitivity, carbon-13 NMR sensitivity by a factor 4. That factor 4 is just gamma ratio, but that has a spin population consideration in there. If it were not for these homonuclear couplings still active and can pump this and so on, you actually wouldn't expect a factor 4. You would have less because you can only have half of the 1 protons coming over to you. Right. Okay, so now I'm ready to talk about the cross-polarization. You see how this works. This is fun. It's a little bit more work, but we have built our step-by-step case. So what's special about CP is you're doing 2 simultaneous continuous irradiation. The irradiation on the source spin, the proton, is really spin lock, and the irradiation on the X spin is kind of like spin lock, although you might say, well, I don't have magnetization initially on the rare spin carbon, so you're not locking any spin in that sense. It starts from 0. So anyways, you have continuous irradiation. All right. Carbon. And the condition for cross-polarization is that the rare spin, the S spin, field strength, omega 1 S is equal to omega 1 I. Okay, you have to make them the same. So that's the Hamiltonian condition. And otherwise, the direction of the spin lock on the recipient channel doesn't matter. It's decoupled, a separate consideration from what happens on the proton side. So this can be anything, but the proton side has to be a spin lock. And so if you started out with a 90-degree plus minus Y, you really have to do either plus X or minus X. And usually we phase cycle to be both directions. So this is what happens at the condition for cross-polarization to actually work. And so now let me show you how to calculate and prove that there is a polarization transfer by doing this. Okay, so condition for CP is omega 1I equals omega 1S, Hamiltonian matching condition. So again, I want to transform my laboratory frame heteronuclear dipolar coupling into the interaction frame defined by these 2 simultaneous pulses. The I spin lock will only affect the IZ term. So IZ acquires this time dependence, cosine sign with IY sign. The S spin will be impacted by the S spin continuous irradiation, and it's going to toggle. And so SZ cosine SY sign. And at first, you should write the frequency of the oscillation separately, omega 1I, omega 1S. But then because of my Hamiltonian matching, these 2 are the same. So that's an important step. If you don't have that same, it wouldn't work out. Because they're the same, there's the same omega 1, then I can start to multiply. I get collector terms, IZ, SZ. Now, instead of cosine omega 1IT and cosine omega 1ST, I have cosine square omega 1T. That's very important because you can see that there's going to be finite non-zero terms coming out. I have IY/SY sine square omega 1T, and then again, I have cross terms, but now you know when you have cross terms, cosine sine, it's going to average out to 0, drop out the calculation, and I would only have the same directional spin operators, IZ, SZ, IY, SY coming out. There's the time averaging, so make sure there is 1/2 coming out. And so the average heteronuclear dipolar interaction now is IZ/SZ plus IY/SY, and then the omega D is in front. Now, how does this look different from the normal laboratory frame? Well, it is very different. You know, the normal laboratory frame is just IZ/SZ, and actually, I don't know why I didn't write this, but normally the truncated form of the heteronuclear dipolar coupling has a factor of 2 in the front. Of course, depends on how you define omega D, but for pedagogical purpose, it's better to keep the 2 separately in the front. Or you can think of it as, if you like, it this way, 2 IZ/SZ. You can also link this to the homonuclear dipolar Hamiltonian because there you have 3 IZ minus I dot I. And in I dot I, you have a minus IZ term. So it's the same amount of ZZ, the 3 IZSZ minus IZSZ from the scalar product. So it's 2. And this 2 is important to keep in mind. This is the lab frame. And after I do the double spin log the CP, that 2 drops out. There's a factor 2. And in addition, of course, more importantly, you've got the second term IYSY. All right, this looks complicated. This is not the same as the laboratory frame heteronuclear coupling, but that's okay. And we're going to show you how this somewhat complicated looking Hamiltonian actually is going to pump the magnetization from the I spin to the S. That's the goal. So first, this average Hamiltonian is non-zero, which is great. And now I actually need to use a little bit more of the average Hamiltonian theory because I need to push the density operator forward. So in the beginning of CP, this means right after the 90-degree pulse, this point, I've already applied a 90-degree pulse on the proton channel, the I spin, and I've chosen the minus Y. So if I keep doing left hand, and so you know the magnetization is going to go to X. Okay, so if you do Y pulse, minus Y pulse, your magnetization will be along this direction. That's your I spin magnetization. Right. So the question is when you have an average Hamiltonian that has these spin operator terms, would you get something that involves a spin, single quantum magnetization? Direction to be determined. And you probably already can guess that you're never going to lose completely the I spin. There will be some I magnetization hanging around just because of the nature of these things. You don't completely lose the source magnetization. So you will have some kind of IX left, but question is, do you get any SX, right? So that's the question. So IX is my rho 0, and I would like to figure out rho of T. So let's break down the IX into a sum of 2 terms, IX plus SX and IX minus SX. This kind of a decomposition is quite useful, and if one works through the fictitious spin 1/2 formalism, one can get a little fancier and see these things a little bit more, but I don't have to do that, but I can just make a note that IX plus SX is a double quantum operator along the X direction, and the IX minus SX, it belongs to the 0 quantum space, and it's a vector in the 0 quantum space pointing along the X direction. Okay, but it doesn't matter. We can stick to these normal spin operators. So now the point is I'm going to take the average Hamiltonian, HIS tilde average, and work out how that's going to evolve my density operator, rho. And so I need to do this von Neumann equation solution treatment. I need to do a single commutator and then a double commutator. So when I do the single commutator, IZSZ, IYSY here, and then IX, I work out how that should be. And to remind you of the mathematics, when it's a completely different spin, you can always take it out of the commutator. Don't worry about it. You only do commutation of like spins. So IZ, IX will give you IY. That's what you see here. And SZ comes along, gets multiplied, doesn't change. And then the second term, IY, IX will give you IZ. And then the SY comes along, gets multiplied. That's what you get. And then you do the second step double commutation. You have to take the same average Hamiltonian and do the commutation with this thing that you just figured out. So this gets a little lengthier, but still not too bad. And when you see the same spin operator, for example, IZ, then it becomes square, and square of any spin operator is a number. It's 1/4. So that gets simpler. Okay, so you work out all of these, and the bottom line is IX minus SX. But you have an omega square, the dipolar coupling constant square coming out. The spatial part of the Hamiltonian doesn't get involved in any of these commutations because it's not a spin, right? So you have to keep track of that. But that's interesting because at this point you get IX minus SX. Now, if you remember the rule for applying the von Neumann equation solution in a sinusoidal series is that you have to have the double commutator coming out to be proportional to the time 0 density operator. We had that condition to plug in. Now, this is not exactly proportional to the whole thing, Ix, but it is proportional to the half part of the initial density operator. It's exactly the same as this subtracted difference spin operator. So that's still useful. What this means is that this averaged heteronuclear dipolar Hamiltonian under the effective double spin lock will evolve the difference magnetization forward. It will not touch the sum magnetization. And so what happens then, I can write the rho difference T, if I just consider that. It's going to be equal to rho difference times 0 cosine of omega dt. And then I have this commutation result, IYSZ minus IZSY. That collects, oh, this is a typo, it should be sine omega dt. So this is all fine, but then you say, well, my initial density operator has this other part, and this other part needs to be added back. So it's 1/2 Ix plus Sx plus the difference. And then you regroup the term, you find that actually very nicely, it's 1/2 Ix, 1 plus cosine omega dt. And then for the S spin, you get 1/2 Sx, 1 minus cosine omega dt. And then you have this part. And this part, it doesn't even matter very much in a sense, because these spin operators, products of two things, they're not observable. So what you detect in the end, what you really care is the Sx. So now what's really satisfying in this is if you look at the result, the Ix gets modulated by 1 plus cosine, there's a half there. So it makes a lot of sense. Rho T is 1/2 Ix. This is my proton, cosine omega dt. Right, so this is the dipolar coupling strength. And then there's Sx, 1 minus cosine omega dt. And then I have terms that I cannot detect. Right, that doesn't matter very much. So, okay, what's 1 plus cosine and then half? All right, so again, I can draw geometric sinusoidal oscillations. Cosine starts like this. And if you do half of it, well, first you have to add this. Let me shift this whole thing. So this starts with 2, the whole cosine shifts up. And then I'm going to do half of it. So I'm going back down to regular situation, right? So, okay, so that's the term in front of that modulates Ix. So you say, okay, does that make sense? That makes a lot of sense, because at time 0, all my magnetization is on the proton side. I have nothing on the S. When I do 1 minus cosine omega t, I have to first flip this and draw this. And then I do the same shifting. I go up, right? And then I do the same half, and you know what I'm saying, right? So the end result of that is for the S spin, I grow from nothing, and so I better, if I have to be very careful, then I need to be opposite phase. So the S spin magnetization grows in time, at time 0, nothing, and when you have nothing on the I spin side, that's when you get maximum, as you would expect. So this is very nice. The magnetization periodically pumps from the I spin to the S spin and it goes back. So if you have a very simple system, literally just 2 spins, this is what you should detect by doing CP. So I can also, of course, if I do half angle relation, you'll find that this 1 plus cosine divided by 2 is basically a cosine square function. If you just have 2 spins, yes, you can pump the magnetization completely to the S spin side. Okay, so we've managed to transfer magnetization, polarization to the S spin, but then there's still an issue of sensitivity enhancement. Now, this is the part where you have to not ignore the prefactors in front of all of these spin terms in density operator. And I want to remind you, we started magnetization on Ix, and I spin has its prefactor gamma I B0 over KT, all of that stuff. B0 field dependence, temperature, and all that. So gamma I is going to be a high gamma spin proton, and this gets tagged along for the whole calculation. So now by the time you have Sx showing up, it's going to be multiplied by gamma I B0 over KT times Sx. Now this should look weird to you because anytime you do normal, excitation on the S spin, you should have gamma S V0 over KT times S whatever, right? So this is where this gyromagnetic ratio comes in, and you copy the gamma from the I spin to S. All right, so this is why we have a sensitivity enhancement factor of gamma I over gamma S. So I have notes on fictitious spin 1/2 operators, but I feel like I want to skip this. The zero quantum space, double quantum space, operators between these two spaces always commute. So the square bracket will come out to be 0, and spin operators in the same space, they will commute in the same way as the Pauli matrices. The regular spin 1/2 operators will commute, xy going to z, and the permutations thereof. Knowing that is somewhat helpful. I find for even just for CP, it kind of simplifies the calculation a little bit, but you have to remember the whole alphabet of how the single spin operators transform into these two spin zero quantum, double quantum operators. Formally speaking, whenever you have I plus and S minus, that's the zero quantum, and you have I plus and I minus, that's the double quantum. And any of these plus minuses are raising and lowering operators, which I should define. I haven't really defined it, but that comes from simple regular spin operators in this way. So raising operator is combination of Ix and Iy with a plus sign in the middle, minus lowering operator is just this. So now if I say, all right, I'm going to somehow combine two spin product operators in the raising and lowering sense, what does that mean? That's why I can spell out these things. And it can be shown if you do 4x4 matrices, because you're having the product operators, then you can do the linear algebra and say, aha, this is true, that Ix of the zero quantum space will commute with Iy of the zero quantum space to give you the Iz of the zero quantum space operator and all of that stuff. And why do we care about all of this? If you are familiar with this, then you can start to see some of the CP average dipolar coupling Hamiltonian. So things like IZSZ plus IYSY kind of shows its face in terms of these fictitious spin 1/2 operator. Actually, you still have to do a rotation, but there's some amount of insight that one can get. Lecture 3, I want to skip the majority of how to understand dipolar decoupling and recoupling, except for Redor, because Redor is very intuitive to show, and it gives you intuition for how to think about the other recoupling sequences and how to analyze them by average Hamiltonian theory. So I want to skip all of the Wahoo-Ha stuff. I was waving my hands in the air to give you an idea. Why do we care to have the average Hamiltonian? Because people wanted to understand how to think about the average local spin interactions in the presence of these discrete pulses with a certain combination of phases. So that's pulse propagators, move them around and show that they're cyclic and etc. So I want to skip that. And with 8 is just double the Wahoo-Ha. Okay, Redor.